Good afternoon, everyone. Welcome to our talk. We're here today to talk about Karmada in action, specifically how you can use Karmada to overcome the massive challenge of scaling AI workloads across multiple Kubernetes clusters. My name is Tessa Pham. I am a senior software engineer at Bloomberg, and joining me today is my teammate Wei-Cheng Lai.
Hi, I'm Wei-Cheng Lai. I'm the software engineer at Bloomberg, working on AI platform.
Hongcai Ren, who is our Karmada maintainer and expert, couldn't join us today, but we're excited to walk you through all the Karmada 101s and 201s today. So the question of why we want to run AI workloads on multiple clusters is no longer new. First, AI models now are huge, and they are critical parts of applications. They are production services, so it requires multiple region high availability for continuity during any disaster. Secondly, when you run multi-cluster strategy, you can solve the challenge of low latency, because right now real-time AI inference demands very, very low latency. You need to use geo-distribution in order to have your model server as close as possible to the end users or to the data sources. Third, we want scalability and cost, because we need to handle spiky demands by being able to burst capacity and utilize cheaper resources across different clouds to save costs. Next, we'll get to centralizing management of diverse and expensive hardware, like A100s and T4s. With a multi-cluster management, you can pull them into one logical resource view. And finally, by diversifying your hardware and cloud providers, you can use multiple clouds and even on-prem simultaneously to give you the infrastructure independence and avoid vendor and platform lock-in. Multi-cluster strategy now is used quite widely for two key AI use cases. One is distributed training. So if you have a really large model that you want to train parallelly across clusters, or if you're running your inference services and you want to serve that model globally in different regions. While the idea of multi-cluster AI workloads is very tempting and appealing, we do run into massive challenges. The first one is obviously the operational complexity. It is hard to manage independent clusters, including upgrades, patching, monitoring, and it is quite labor-intensive to do so manually. You will have to worry about synchronizing all the configs. So you need first consistent configs like RBACs, network policies across all clusters. And if changes are made to the configs on one cluster, then it can easily lead to drift over time. There are also difficulties in making deployment and scheduling decisions. How to decide where to deploy a workload based on several factors: capacity, cost, latency. You will also lack a unified resource view if you just rely on individual Kubernetes schedulers, because they're cluster local. So you cannot see the total real-time pool of resources that you have across all clusters, and that will prevent you from being able to make optimal decisions to schedule your resources. And with that, it's also hard to do automatic scaling across clusters. If your platform is currently relying on standard HPAs, which are also cluster local, then it's impossible to burst your workloads seamlessly to other clusters without interrupting your workloads when one cluster runs out of resources and you have to find capacity somewhere else. Handling dependencies between clusters and between services clusters also comes into play, and that can be hard as well. And finally, with policy and governance, like syncing configs and syncing policies, like I have talked about before, that is a headache to manage. Now, on top of these general multi-cluster challenges, they are magnified when you deal with AI inference. some unique challenges to inference is one, critical latency and so when you run inference, you do require sub-millisecond response times. And with that, you will have to think about where to place your workload. And you have to be very latency aware with your traffic routing. Now, when you have very large models to serve, and you run the models on multiple clusters, how do you distribute them, and how do you keep track of their versioning, right? And next, AI models now are become way more complicated with very specialized hardware. And it's very rare that all of these hardware GPU types like T4s, A100s, TPUs, it's very rare that they exist in just one cluster. So with the heterogeneous hardware, how do you manage scheduling your inference services or your models so that it lands on the cluster that has the hardware requirements? And finally, with inference, you do run a lot into very rapid, unexpected, spiky demands, and that is unpredictable. So then your platform needs to be able to handle this dynamically by being able to burst it into other clusters. And so in this talk, we want to talk about Karmada as a solution to our multi-cluster headaches. If you're here, you're probably already familiar with Karmada or wanting to learn more how Karmada can help with your platform. It provides a centralized control for by having a unified endpoint to deploy and manage applications across all clusters. Karmada is essentially a multi-cluster scheduling platform, so it can intelligently place your workloads based on available resources, labels, or any policies defined by the users. And with that, you get high availability out of the box with its automatic failover and ability to reschedule upon any failures of your clusters. Karmada also offers cross-cluster auto-scaling, which Wei-Cheng will also talk about later, but it can automatically adjust the number of replicas across clusters based on demand. And this will also handle the spiky demand problem that we mentioned before. And finally, it is built on top of Kubernetes, so it is interoperable with Kubernetes. It acts as a Kubernetes API endpoint and therefore easily integrated with other tools and resources within the ecosystem. Let's go over the high-level architecture of Karmada. First, we have the control plane. So this is the central brain of Karmada that has the API server, and there's a controller manager that manages multiple controllers, and there's the Karmada scheduler that will make the scheduling decisions. And outside of the control plane, we have member clusters, and these are standard Kubernetes clusters managed by Karmada, and this is where your final workloads will land on and run on. For a deep dive into the architecture and also the core concept of Karmada, I have linked here previous talks at KubeCon that we do go with more details into the architecture. But today, we want to dive more into the policies and also some new features of Karmada, and also Karmada for inference as well, as we have seen it being used more in the past year. So multi-cluster scheduling. In this diagram, let's assume that we have a given arbitrary resource called training workload. This is not a native Kubernetes resource, so it will need to be interpreted in order for Karmada to understand. You do this with a resource interpreter. After interpreted into what's called a resource binding, the Karmada scheduler will take this resource binding and go to propagate. If the resource has dependencies and in the propagation policy, you set the propagate depths to be true, then it will try to sync the dependencies of these resources first to the member cluster. And then it will go to propagate the resource. And before the resource actually lands on the member cluster, there is customization that you can further use to fine-grain to control, have more fine-grain control over what the resource looks like when it's federated. And finally, in the case where the current cluster cannot handle the current workload or it fails, then we have rescheduling and failover. Quickly, on resource interpretation, Kubernetes is very extensible with CRDs, but that also means that Karmada will not understand your resource if it's a CRD. So you will need to write an interpreter to tell Karmada how to interpret it into replicas, into the dependencies, and how to interpret the status. And that's essentially what it does. It identifies replicas, dependencies, how to aggregate the health status across all clusters, what it means for it to be healthy and running. There are two types of interpreters. You can write a resource interpreter customization, which is a YAML. And in that, you can have a Lua script to basically translate one-to-one, do a one-to-one mapping of your custom resource to what Karmada understands. Or you can write a custom webhook to do this interpretation. So yeah, in this diagram, you can see this resource will go to the interpreter and gets translated into this blob right here that Karmada will understand and will federate the resource accordingly. So as you can see, Karmada offers a policy-driven orchestration. Scheduling decision is guided by propagation policies. And then next, we'll have, before the resource actually lands on the cluster, you'll have override policies. These are optional, but you can further customize the resource. This will tell Karmada what to change about the resource before it lands on the cluster. And in the case of, again, the current cluster cannot accommodate the resource for some reason, then Karmada very smoothly does cluster or application failover or rescheduling of the application. So the propagation policy answers the question where and how to deploy the resource. The example here, I'm using an inference service. I want to gear this more towards inference. But basically, this is a very simple YAML of an inference service that serves the this PyTorch model called GPT. Right? And these are all the resource limits and requests. When you bring this to Karmada and after it gets interpreted and then it gets brought to Karmada, Karmada will use the propagation policy that you define and answer the question, okay, where can I put this inference service? What cluster would serve it best? Or what clusters cannot serve it? So you will use the cluster affinity field to select the clusters. You can also use tolerations to exclude clusters if you want to reserve those clusters for something else or for specific teams. There are dependencies to tell Karmada whether to sync them first, the member clusters. Spread constraints can be used to evenly distribute the replicas based on topology. So you can distribute it over regions or zones. And finally, the replica scheduling strategies. You can either duplicate a set of replicas or divide the total number of replicas across clusters. And you can also assign it priority so that it divide based on, there's a weighted division. So some use cases for AI workloads, our adopter ScatterLab, they use Karmada and they are deploying the AI chatbot using the cluster affinity to deploy them to 2 clusters in 2 different regions. And that allows for multi-region HA and low latency. You can use affinity to do hardware-aware scheduling, so only landing the resource on the clusters that have that hardware requirements. There's weighted replica distribution. So again, giving priority to the primary regions or to the primary cluster so that it receives more replicas of your, say, inference service than the secondary region. Cross-cluster automatic scaling can be used when you use it with federated HPA and with the dividing replica strategy, so then it can scale up and down and using that priority that you gave it. And finally, you can also version models with cluster affinity to target environments with different model versions. And the override policy specifies what to change about the resource that lands on the member clusters. For example, here we have two different clusters. Cluster B is on-prem, and it has CPUs, and it has 8 A100s. And cluster C is the AWS, and it has 8 L4s. So before the inference service lands on the cluster, you can modify it, modify the image path. For example, this storage URI right here. You can modify commands, args, labels, annotations, plain text, or even fields. So if you want to be more conservative with the cloud provider cluster, then you can have lower number of replicas and have it scale to 0 when there's no traffic. So a few use cases for override policy for AI workloads is one, canary rollouts. You can modify the container image to deploy a specific version to specific clusters that are running, say, the blue deployments. And you can also do overrides for GPU and hardware by injecting structural fields like node selector or tolerations for specialized hardware of the cluster. And make specific configurations like model or image paths. And finally, adjusting the resource request and limits. And you can do that with override policy as well, as I have shown in the previous slide. So now I'm going to hand it over to Wei-Cheng to talk about federated HBA, resource quotas, and cluster failovers.
Oh, okay. Yeah, thanks, Tessa. And building on their foundations, let's look at why quota management gets tricky in real multi-cluster AI environments. So first, every region looks different in multi-cluster environments, and hardware might mixes vary in GPU counts, CPU, and memories. And this difference change over time as we add or retire nodes. And now if we try to reuse a single resource quota template across clusters, it quickly breaks because a quota size for a region with 4 GPUs, for example, won't fit a region that only has 2. You either underutilize a large cluster or fail admissions in a smaller one. And today, many teams paper over this by crafting per cluster quotas and pushing them with their own workflow or with Karmada's propagation policy, then patching them per target with override policy. And it works for a handful of clusters. However, this becomes a policy sprawl at scale. Dozens of near duplicate objects, constant overrides, or manual recalibrations whenever capacity changes, and that leads to configuration drift, noisy alerts, and there are also maybe some jobs were starving in one region while resources sit idle in another. So Karmada provide a lightweight fix. It provide a feature called FederatedResourceQuota. And instead of headhunting quotas in every region, you can create only one single federated resource quota per namespace. And in that object, it will list how much each cluster should contribute with the static assignments, and it will also shows the aggregated usage and hard limit for each clusters. So from there, Karmada will fence that single intent out and creates the normal Kubernetes resource quota objects inside each member clusters. And the admission for this feature, the admission still happens locally with the native resource quota. And what you get is you only need to define one resource, and it will distribute it everywhere without babysitting a pile of per cluster policies. And you also get the visibilities such as aggregated resource, so you know which cluster how many of each cluster use, and you don't need to hunting through dozens of objects or dashboards. And this is actually nice for heterogeneity. For example, if region A has 4 GPUs and region B has 2, and you can capture the difference in the single resource, and you don't need to continue checking each of different resource quota. So then you get a single source of truth and zero policy sprawl. And And for more advanced usage, we also provide another feature-gated features called federated quota enforcements. With it on, you can define the global hard limits in your federated resource quota. And you don't need to have pre-slice those limits per cluster. So here's the flow. Like a user submits a workload to the federated control plane. And before the scheduler finds anything out, Karmada will run the quota validations against the federated resource quota. And it looks at the current aggregated usage. The federated resource quota controller will aggregate all the usage up to the Karmada control plane. So in the controller, it will know the current aggregated usage. And if the total exceeds the namespace global cap, the create or update will be rejected immediately. So nothing will propagate to member cluster, and you can avoid like noisy rollbacks or partial placements. And to keep that check accurate, like Karmada will continuously synchronize that. So and without any extra configurations. And the validator and scheduler will both rely on that information to make sure the resource is correctly used and guards. So this gives you like the fail-fast protection against oversubscription. And you get far less per cluster tuning and consistent quota behavior across heterogeneous regions. And next, like in some cases, when the cluster runs even hotter and quotas don't answer the questions like who run next, you might need a more advanced and global admission multi-cluster queue, where jobs from every region line up and are handled by priority, fairness, and capacity, not just by whichever cluster is least busy. And Karmada and Volcano has collaborated and provided Volcano global features. It builds on top of Karmada and stretches Volcano's familiar jobs semantics from one cluster to many, aimed at large-scale AI training and inference. Feature-wise, you get cross-cluster scheduling and queue priority, job priority, and capacity. So scarce GPUs go to the most important work, while tenants still receive fair share. And in summary, this gives you like a single policy-driven admission layer on top of the Karmada, and it provides priority-aware and capacity-conscious for you. And next, let's talk about like the auto-scaling. The native Kubernetes HPA is excellent within a single cluster, but it only watches signals. It only watches signals as CPU memory or custom metrics, and asks the scheduler to add or remove replicas in the single cluster, in the same clusters. But in multi-cluster AI environments, that scope normally becomes a hard limit, because the bottleneck isn't the target value on metrics, it's GPU availability. And when the region is hot, for example, when nodes are full or quotas GPU limits are reached, the HPA can request like more replicas, but they will sit pending because there is simply no room to place them. Meanwhile, another region might have plenty of headroom. Native HPA has no mechanism to spill over to the other clusters. And the outcome might be queues and throttling in the hard region and idle capacities elsewhere. And you will need a lot of manual intervention or over-provisioning to compensate these situations. And this sets up the need for something broader. And let's talk about it in these slides about federated HPA. So in Karmada, the federated HPA runs in the control plane and reads metric through the standard Kubernetes APIs. And the Karmada metrics adapter scraps each member cluster and aggregate those metrics and rolls these numbers up, and hence the controller one federated view of across the clusters. And from the picture, FHPA can decide on a single desired replica count for the workloads. And Karmada scheduler can place those replicas on the cluster that still have headroom. And this feature especially works pretty well with the propagation policy, because when federated HPA calculate the desired replicas, when Karmada is doing scheduling, it still consider the propagation policy, the policy that we define. So you can Karmada can scale those based on maybe weighted policies or like the toleration policy that you have defined. And for AI inference, normally the simplest one might be from the getting metrics from the applications and to measure like requests per second or time to first token. And you can simply use measure this like you are using a single cluster HPA. You can just use Prometheus adapter to export those, and Karmada metrics adapter will fetch those metrics on the Karmada control plane. Or you can also use a GPU-based policy, like fetching GPU telemetry from DCGM or like from your third-party environments. As long as it's exposed from the Prometheus adapter from the custom metrics, Karmada will can get those information from the Karmada metrics adapter. And so in summary, you can choose the signal you trust, either like applications or from GPU or from third-party applications. And Karmada will turn that signal into one decision for the entire fleet. And you avoid like per cluster guesswork, and you can place replicas where there's extra headrooms. So besides the elasticity, let's talk about the reliability that Karmada provides. Karmada provides like the cluster failover features. It will continuously watch its member cluster health through cluster status. And if a cluster flips to not ready or unreachable, Karmada marks it unhealthy and isolates it. So, and also if it can also help evict workload from the unhealthy clusters and then migrate them to healthy clusters. Those are like working out of the box. And recently some of our adopter has some observation on these features. Like they found that the real world is actually messier than we imagined. So the previous cluster failover features is maybe not like cannot meet all the requirements, because in some cases many issues are partial. Like it may be a short control plane blip, or like just a network partition that strains one node pool, or a storage class hiccup, or even just a GPU driver crash on a subset of nodes. So if we use these features out of the box and react the same way to every symptom, we probably might widen the blast radius. We might be like moving too many and too fast, and sometimes even amplify the problem by pushing churns into other regions. So Karmada has provided another new features called to provide fine-grained control over both the failure signals and the TANs we applied. And the cluster 10 policy is that control knob that for the new feature from the new features. With this cluster 10 policy, you can declare when to tend a cluster and when to clear it. Like you can choose the target cluster and also define two rule sets with add on conditions and remove on conditions. And for example, like you can add a 10 when ready is not true and network available is not true. And you can remove the 10 only when both return to true. Those are end matched. And signals also aren't limited to what Karmada computes. You can publish third-party conditions from your own detectors. For example, the cube component health is published from our own service. And Karmada can also match on those as well. And these are a couple of there are a couple of operational guardrails to avoid like surprises. The controller can evaluate every rules first and remove rules second. But if both will match, the removal will win. And if you later delete or change a policy, existing TANs are not auto-cleared. So your operator can stay in control of when an isolated cluster re-enters the pool. So in summary, like this cluster 10 policy gives you fine-grained and policy-driven isolation, which you can plug in with your custom condition detector or writer, and you can Karmada will respond differently from your fine-grained cluster 10 policy. Oh, I think the time is running out, so I'll just quickly go over this. In a lot of cases, like for AI inference, you will also have a lot of dependencies with your applications, and Karmada's application failover can also help you migrate the dependency with your AI inference application, and you can controls what happens to the copy, and you can also define it with the interpreter framework. So you can also bring your CRD with this feature, and you can design your custom definition of your unhealthy conditions. So in summary, like if the cluster is fine but the app is not, you can use this feature, and it will help you migrate just the workload and the dependency of it. So you stay available with our region-wide failover. And so let me quickly read out the playbook. So first, placement. So you can declare what goes where with propagation policy and shape regional differences with override policy. And next, when you run CRDs, you can bring them with the loop with the resource interpreter. And right now, the community also working on supporting like rate services from KubeRay, chain drop from Kubeflow, and also Flink drop. Those are, you can use it out of the box. You can also use it with your custom CRDs. And for guardrails, you can use FederatedResourceQuota. For admissions, fair scheduling, you can use Volcano Global. And for elasticity, Federated HPA can aggregate the metrics across the cluster and help you scale across the clusters. And finally, Karmada plan for failure as a normal case. So you provide cluster 10 policy, application failover for you. And right now, community is also like focusing on scheduling efficiency, control plane efficiency, and multi-component workload support to improve placement accuracy and quota calculations. So, so feel free to reach out us on Karmada Slack. And thanks everyone, and enjoy the rest of KubeCon. Thanks.
Open for Q&A.
I think we don't have time. Okay. Yeah.
Sorry, you have a question?
Oh.
Okay. Well,
Yeah, I have a few questions here. So I'll start with the first one. Since Karmada is essentially a control plane that has to run over multiple clusters, is it recommended to run Karmada on like your CAPI clusters that are already managing pieces of that?
No, we would normally recommend to run Karmada on the single host clusters and then link to the already running clusters.
Okay.
Because Karmada will need to aggregate a lot of information from those member clusters. So normally we'll use some amount of the resources.
Okay, so like let's say I have a control cluster that's using CAPI to say all of my multi-clusters I have over multiple clouds run the same version of Grafana. You wouldn't want to put Karmada with that CAPI cluster. You would want to create a whole nother control cluster that would reach into all those other ones too. Is that correct?
Sorry, can you say it again?
So to just put make an example, if I have a CAPI cluster that manages my services in all my clusters, my worker clusters,
Yep.
would you put Karmada in that CAPI cluster, or would you create a whole nother cluster for CAPI to reach into all those other clusters?
Like, you mean heavy cluster? Like,
CAPI is in the cluster. Oh, I just blanked on it. Can someone help me on that one? I forget what is it?
there's a heavy cluster. Is
The cluster API, cluster API cluster.
he has like a host cluster to control like worker clusters. So
Okay.
now where does he install?
Oh, like, I think it depends on like it depends on a lot of cases, like your availabilities or your how large your host cluster is. If it has enough resource, you can just put Karmada cluster on that resource, and that it manage all the member clusters.
Gotcha.
And also, you can even run it like active. You can have like two Karmada cluster running on two different host clusters, and they can work together. Because Karmada is also designed as like is also support active deployments.
Awesome. Well, you answered my next question. And then my following question is, because these CRDs require interpreters, is there a place like Artifact Hub that I can find these interpreters, or are those all custom, or how would I go about finding interpreters that are already written by the community?
Sorry.
Where can you find the interpreters that are already implemented by Karmada?
Oh, yeah, you can. There are a lot of examples in Karmada repository for custom resource, and maintained by the communities. And we also provide like a playbook for how you implement your own interpreter
Gotcha.
for those CRD.
And then my last question is, since we have a bunch of clusters that would be essentially running the same workload, is there a concept of like bulkheads or blast radiuses with Karmada or something that you're working further for other than just the cluster taints that you're working towards now?
Oh, I think there are some of the. I'm not pretty sure about that. I can get back to you on that.
Okay.
But some of the maintainers are working on enhancing that features as well, like adding more taints, adding more different kinds of taints, like not because currently we only support like no execute, no schedule, and right now they are also working on adding more taints to support like more fine-grained and more complex cluster failover scenarios.
Gotcha.
Yeah.
Thank you.
Yeah, there's actually issues that you can follow up on Karmada repository about the cluster failover features. Yeah, we're happy to hear your feedback on that. Yeah.
Awesome. Thank you all so much for coming and listening. And thank you for the questions.